Hello, we're a team from Turkey, and we've done a project on a quantum algorithm implementation for high energy particle physics simulations. Um, and we're a team consisting of 3 high school students. My name is Duru. My teammate here is Shifika, and we have another teammate. Her name is Lauren. So we learned that a lot of extremely complex and high consequent experiments are done on the field of particle physics. And because these experiments are very costly, a prediction is required beforehand to have an insight on the experiment. So it's possible, so the possible results and the resources required so that there wouldn't be any precious time or precious materials wasted. The reason why this is better done on a quantum computer is that classical algorithms are insufficient for representing the quantum effects to a full extent, while quantum computers are more fitting for experiments done in particle physics.
So why did we choose this project? As a bunch of high schoolers, I think the best way for us to find the project was to go to archive.org and open every single quantum computing paper we could find until our computers crashed. Um, and when we looked at those papers, one paper stood out, and that was the paper about high energy particles because we could saw lots of potential there. We could see that it would teach us lots of things, such as quantum field theory, such as the quantum effects of collisions, and that was very very interesting for us. Then we read the whole paper and tried to understand it. Here you can see the circuit that was proposed in the paper. And our circuit is actually very similar. And our motivations are also similar. We want to show the effects, the quantum effects, without the costliness and without the difficulty of classical algorithms. So in our circuit, we used controlled knot gates and rotation gates on Y basis. And the reason we chose those gates were that we thought uh, that we found out they worked in small amounts of numbers. For example, when we had just a couple of qubits, they worked very well. And these, if I were to explain those qubits, so P means particle, H means history, E means emission, and N means number. What those qubits do is basically um, P does P is the particles, H is the qubit that we store the information, E is our qubit, which shows us if there was an emission that was occurring or occurred. Lastly, N shows us the number of particles. Uh, so when we look at the first step, we can see a rotation. In the second step, we count how many particles are there. In the third step, we determine if an emission occurred. In the fourth step, we see if a particle chose to radiate and branch. In the fifth step, we update we update the particle. We update the history qubit, for example, to store our information. And lastly, we rotate back to our initial state. And is our results. And the conclusion will be explained by my dear friend, Drew.
So overall in this project, I think we learned a lot about how the universe works, in especially like in really small particles, and we learned a lot about what a Markov chain is, what a Monte Carlo method is, which aren't usually stuff that high school students know about. We learned about the perturbation theory, the quantum field theory, and some terms like intermediate particles, and some of the properties of the standard model. And I think this has really helped my understanding of how the world works, how the universe works.
Thank you for listening.